Like many people watching, for me it all started when a friend showed me that video from France. I thought, A, that looks amazing, and B, I want to build one of those. After some initial research, I decided to use the Bebop as a platform, and I would start working on the software side. The Bebop had an easy-to-use API and was supposed to be easy to fly. It also featured an onboard GPU, which I'm sure could be interesting down the road. It also allows me to send digital video directly to a computer where I could further process it. For that processing, I went with a Samsung Galaxy line, although my initial development was done on an LG G3. With the smartphone, I have a platform where I can process the video and sensor data from the drone. The Samsung phones also allowed me to use the GearVR headsets as viewers. The touchpad allowed us to use gestures to change settings and the responsiveness of the drone. Initial test flights were conducted with first just a video feed, and then later with head tracking and a basic HUD. They were incredibly challenging, although drag racing was still really fun. The live feed from the drone undergoes real-time compression based on network conditions and is also sent in standard definition. This could create images that appeared flat and with very little saturation, which sometimes made it difficult to see spatial cues and accurately estimate depth and distance. The video was also initially only stabilized, so estimating the state of the drone was near impossible. We found head tracking in particular drew so much of the pilot's attention that it added its own layer of difficulty, and we ended up making it optional. The early versions of the HUD at the time were, while helpful, did little to make us better pilots. My test pilots and I were extremely crash prone, and we quickly learned the Bebops were as delicate as flower petals. I started doing more research on information display in situations where safety is a concern and where there are high speeds. It led me to various pieces of research by NASA and others on head-up displays for everything from commercial airliners to helicopters to the space shuttle. After watching hours of HUD footage, I started redesigning my racing HUD. The goals of the HUD were to, first, aid the pilot's drone state estimation, especially at high speeds. Second, to provide directional guidance. And third, provide status information about the drone. We found having the HUD appear in one eye allowed the HUD to be less distracting and allowed the pilot to see through the HUD. Special attention was given to graphical elements and calculations that improved situational awareness and aided in state estimation while maintaining forward visibility during high speeds. The interface layout focused on keeping primary guidance information within about 3 degrees of the pilot's gaze in the primary guidance information cluster. Secondary guidance information within 10 degrees, and redundant and drone status information in positions selected to avoid image clutter, but within glancing distance from the image center and the pilot's traveling gaze. In testing, I found through pilot feedback that our pilot's gaze will most likely be closely following one of two things at any given moment during flight: a landmark that the pilot has temporarily designated as a waypoint, or the flight path vector, which is part of the primary guidance information cluster. The flight path vector is also referred to as the FPV. Flight path vector, which we like to call the birdie, gives the pilot about a 1-second advanced estimation of trajectory. This allows her to better estimate where the drone is going to be and gives her additional time to course correct if needed. When I first implemented the FPV, we were still crashing fairly often. It was marginally easier to fly, but we were still crashing, especially on higher speed turns. Then one day I decided to trust the birdie. You see, in earlier tests we found we used the flight path vector as a guide, but mainly relied on visual cues from the video feed to estimate the required stick input. When I kept my eye on the birdie, I noticed I could then easily guide it to where I wanted it. Previously, we concentrated on aligning the hardware in the direction we wanted to go, which meant focusing on the different attitudes, yaw, pitch, and roll, and hoping we were lining them all up with the vanishing point. When we simply guided the birdie to where we wanted it to be in the image, the drone started ending up where we wanted it to be in the space. If you've flown first-person view, you know what I'm talking about. The other revelation was that if the vector was not pointing at an obstruction that was in my line of sight, I could be pretty confident that I could maintain course and not strike that object. I could fly with confidence now that it was suddenly easier to avoid crashes. Pay special attention to the grid pattern of the window. The FPV directs the pilot's eye to the vanishing point during forward motion. I have yet to be able to perform any meaningful scientific test, but for us, we've experienced a dramatic improvement on our ability to fly and fly faster using this head-up display. This is roughly north. There's going to be another area right up here, right in front of me where that brown stuff is. And around here, get a little magnetic pole. So up at 81. And then subway north is behind me. Walking, there it goes.